Hello again, and welcome to AP Calculus AB. And our lesson today is 7.2C, or figuring out volumes of known cross-section. I really do like this lesson, and hopefully we can have some fun and some challenging time together. So let's get started. So we're looking into our textbook. We got this little section on solids with known cross-sections. And I really do like this little section here. Notice we've got two different models. One, the sliver or cross section is going this way. Another one, the cross section is going this way. Now, obviously, we're building squares, and we're going to go from the biggest square in the back to the smallest square in the front. So obviously, that would be a delta y. In this case, it would be a delta x. It depends upon how you set up your diagram, and you want to use common sense in how you set it up. But the main reason I'm pointing this out is that you're using basically two formulas. So if you're using delta x, then you're going to go from A to B, and then your function needs to be in terms of x, because dx is your width. That makes sense? And if we're going to use the y, like in this part right here, then if dy is your width, then your variable of integration has to be y. So you have to make sure that you solve your function in terms of y. Anyway, we'll explain that on a couple problems. So let's just do a little illustration first. Hey folks, I tried to get some software to give you a visual of what we're doing. Let's see how this goes. Okay, we're going to try to do a little example. Here's an example of circle. We got little chords going here. We're going to drop our axes a little bit so we get a little picture. And let's put 4 squares. So our cross section is going to be squares. And we could sweep. We could sweep a square from the left side all the way over to the right side. Our solid. Okay, so here we're going to create a solid. That's what the solid would look like. Again, this is called volumes of known cross sections. Okay, so it's kind of neat, and it really helps you visualize what's going on. Okay, so we're going to try this with another. Okay, so this is, we're going to do triangles this time. We're going to drop our axes, equilateral triangles. We could sweep the triangle. Remember, we're using the upper and lower value of the function to describe the base of the triangle. We can create our solid. When you think about this, manufacturing items, packaging, making items in engineering, very important. Let's take a look of maybe like semicircles. So there's a triangle there. We want to see what it would look like with semicircles. So let's create the solid. So we started at the 0 mark, and we're moving toward the front. Here we could show the picture with little triangles here, little semicircles. Sorry about that. Let's try one more. So these are right triangles, and we're building our model, kind of like a 3D printer. And you could use this way of using proportions to be able to come up with your equation and then use it in your integral. It's really a pretty good idea. But anyway, those are some visuals I thought you may be interested in. Okay, folks, we're going to do 2 examples. Remember, this video can only go to 15 minutes, so I'm just not going to waste a lot of time. Example 6. Find the volume of the solid shown in the figure. Now notice the figure right here. So it looks like it's a there's 2 lines going this way. This is the x-axis, and it looks like there's a triangle here. See it, the cross section? I've got an f of x and a g of x. So find the volume of the solid shown. The base of the solid is the region bounded by the line. So here's f, here's g, x-axis. X equals 0 is the starting point. The key to this problem is the cross sections perpendicular to the x-axis are what? Equilateral triangles. So we'll solve it, and then you can see how they solved it and compare the two. Okay, example 6. Definitely a free-flying situation here. Here's my x-axis. Here's my y-axis. Okay, now what we're trying to do is, remember we had an upper function, this guy. We had a lower function, that was this guy. Okay, and then we want to build our rectangle. Now remember what happened to the angle then when it got into an accident? What happened to the angle? It became a rectangle. That's exactly right. Okay. All right, so now we're looking down, right? There's the x and there's the y. We're looking down. What we want to do is try to get an idea of what that would look like. So that forms the base of the equilateral triangle, and let's just picture it coming up to us here, right? Okay, so that's the little cross section. Okay, excuse me for the lack of clarity in the picture. All right, so now remember, this is the y, this is the f of x, that's the g, and the height of an equilateral triangle is right there, h. Now, let's review that for a second. We know if it's an equilateral triangle, and everybody knows that the area of a triangle is 1/2 the base times the height. Well, if it's an equilateral, then this has got to be 60/30. So you always multiply the short side by radical 3. That would be b over 2. So b over 2 times radical 3 would be that. So radical 3 over 2 would be the height. Now the question is, we have to use the little integral. What was the integral? The integral looked like this. 0 to some value of x, okay, a to b, okay, times the area times the height or the width. In this case, it's delta x. So that would be the volume of the little piece. Now, so the volume of the whole thing is going to be adding up all of these as delta x gets really, really small. Well, we got to find the area. So area equals what? 1/2 the base, oh, that would be b, times the height, which is radical 3 over 2. But wait a minute, that base b is really what? It's the distance from the f minus the g, okay? And then that's times the height, which is what? Radical 3 over 2. That should have been, the height is radical 3 over 2, b over 2. Okay, well, wait a minute, b was going to be what? F minus g. Okay, it's a little strange. So let's clean this up a little bit. So the area of that piece is going to be radical 3 over 4, f minus g squared. Okay, everybody understand where we got that from? Okay, Hold on. We got that. The area right here, this whole thing's going to equal to 1/2 the base, which is this, which would be f minus g, times the height. What's the height? It's f minus g time over 2 times radical 3, so we don't need that. All right. Second mistake already. All right, well, let's see. What is f minus g? Well, f, according to the directions, was 1 minus x over 2. And what is g? Negative 1 plus x over 2. Well, what would f minus g be? Okay. Well, let's see. It's the top minus the bottom. So that would be what? That would be 1 minus x over 2 minus a negative 1, which would be plus 1 minus x over 2, which gives us 2 minus x. 2 minus x. Remember, that is this little b. So how would I put that all together? I would say the volume is equal to, remember, we have to have the area. It's the integral from 0 right here to where they meet at the x-axis. I believe that's 2, okay? 0 to 2 times the area. Well, what is the area again? Well, it's radical 3 over 4 times f minus g squared. 2 minus x squared. Okay, and our variable of integration is x, so we're going to say dx. Hopefully that makes sense. Now, we could do this a couple ways. One way would be to factor out the radical 3 over 4, okay? And now we have our u would be 2 minus x, so to integrate would be 2 minus x to the 1 more power. But du, well, du would be a negative 1, so we need to put a negative out in the front. And we finished integrating, and we got to evaluate that from 0 to 2. So what does that mean? It's going to be negative radical 3 over 4 times what? Well, I'm just going to say blah minus blah, okay? Now, one of these is going to be 0. Oh, yeah, when we put in the 2, that's going to be 0. So that's going to go away. So let's work this out. Negative radical 3 over 4 times something. Now, what is that something? Well, we have to plug in the 0. So what's 2 minus 0? 2 minus 0 is 2. 2 cubes a whopping what? 8. Okay. We forgot to put out 1/3 in there. Okay. So 1/3. 1/3. Okay, 8 over 3. Which is what? Well, it's negative, right? So it's going to be 2 radical 3 over 3. All right, that should match your book. Remember, it's cubic units. All right, so that was example 6. Pause the video and look at this problem. Okay, example 7 is a great example, and we're talking about developing the formula for the volume of a pyramid. Remember, it's 1/3 the area of the base times the height. Now, I spent a lot of time working on this problem, and I messed up. So I want you to know it's easy to mess up. Here's this problem worked out. Now, I don't know how I'm going to explain it in 45 seconds, but here's my pyramid. Here's my sliver. Here's the volume of my little part. I figured out what this line would be, the equation of this line, and I threw it back into my integral. So the volume is 4x squared delta y, 4x squared delta y. I worked a little magic, okay, integrated, got blah minus blah, put my values in, should have been 0 and h, and got my answer right down there at the bottom, which is b squared h over 3. Remember, b